NanoHub U, online instruction.
Hey everyone, welcome to lecture 422. This is the final lecture which will summarize and conclude Unit 4. So what we're going to look at is just brief summary and overview of all those details of what we talked about and what did they all mean in the big picture. So remember that we'd actually started by talking about photonic crystal laser cavities. And the reason we were talking about lasers in Unit 4 was because, first of all, they're not just a simple matter of optics, but there's also an electronic model, and then in some cases, a thermal model. And these things are all happening at the same time, and they have strong interactions with one another. But first, we just had to establish that we can correctly model the optical aspects of the laser and correctly couple it to electronics. And so this was an example of a Fabric Pro type cavity laser, which is optically pumped. So this is analogous to a VCSEL or vertical cavity surface emitting laser. And we showed that just like in the VCSEL case, you can actually get, for very small input power, very low output power, of course, but then there's a rapid threshold increase. So that's called the lasing threshold, where you have a dramatic increase in the output power. And so that's basically, we said, where stimulated emission starts to dominate your three possible processes, which again were absorption, spontaneous emission, and stimulated emission. And so, of course, in order to get that to happen, you need to have a population inversion. And so that population inversion usually is what's creating that condition, along with, of course, the losses of the system. So the balance between having enough gain from population inversion to balance the loss of the photonic structure that we're dealing with. And so that we showed that we can accurately model all that stuff. And then we showed another method which would be slightly different from the finite difference time domain, but is also very important for understanding not just optics, but also multiphysics problems, which is called finite element, and has been widely deployed by many, many people in the last decades. But we said that the most common approach for finite element method is what we call the Galerkin method. And so we said that the way that we can understand the Galerkin method is analogous to taking a function and then trying to stuff it into a box. And then we get one finger, which is a trial function, for each of the times that we try to stuff it into the box. And so what this is showing on the right-hand side is just if we have a problem and we have an analytical solution, so we know the exact solution, this is good for testing, then if we just have a few of these fingers, and we only allow ourselves to have a linear basis in each of the elements, then there can be some deviation, but we can match exactly like those endpoints. So of course you can see that the more of these fingers or more intermediate points we have, then the better we can match that analytical solution. And so that's, of course, what we typically would refine in what we call a grid-independent study. And there is a specific toolbox that's available for free in MATLAB called Phasor, and you can download it from this website if you want to try it out for yourself. And so then once we establish this basic modeling capability for both electronics and for optics and other types of problems like mechanics, then we said, let's apply this to thermal problems as well. And so for thermal transport, we said there are three basic mechanisms that are very important. Convection, which we said is like when you have a cold breeze on your skin in the middle of winter, and that's where basically the gas or fluid is removing heat from your body. And that goes like this convection coefficient H times delta T. And then we said there was a second mechanism called conduction. And conduction is like when you touch a hot stove and basically heat is transferred through a volume by the propagation of phonons, which are just elementary units of heat. And then we said that this phonon conduction problem can be modeled as so, where we have the rate of change of the heat in the volume subtracted from this basically exogenous heat generation or absorption is equal to the diffusion of the heat, which is given by this Laplacian of U. And then finally, the third transfer mechanism that's the most closely related to our optics understanding is radiative thermal transfer. And that's when you have emission of photons and received by some other surface. So like when you walk outside and you feel the sun warming your skin, then we said that that can be modeled using basically the black body law modified by something that depends on emissivity as a function of wavelength. And then also optionally, there can be dependence on angle as well. But then you need to drop that pi and then perform integration. And we had done that as well earlier in the course. And you can refer back to that in the thermophotovoltaic discussion. Just to briefly recap, like what are the modeling steps for all these thermal problems? And so this is just one example for thermal conduction. First of all, we have to write down our equation. Then we have to define the material constants and system parameters, define the geometry shown here, and then mesh the geometry with our finite elements, create the material object, which basically connects the blocks of cells together, apply the initial conditions to generate the system matrices, and then solve those, both in steady state or over time. Like both are possible depending on the problem. And then we applied these kind of thermal modeling capabilities, both extending from our optics modeling of emissivity plus the finite element modeling of the thermal conduction to actually compare our models to experiments. And then we showed indeed that many of these very sophisticated nanophotonic structures can give us thermal emission that greatly differs from either like a flat piece of tungsten, which is shown here in green, or a black body shown in black, and is very favorable for certain applications like thermophotovoltaics, where we need high emissivity or spectral radiance at short wavelengths, and we need it to be low at long wavelengths in order to get high efficiencies. And then we said that if you combine these structures with what we called integrated filter, then you can get even higher efficiencies than would be possible from the photonic crystal structure alone, potentially as high as 46%. And we showed specific structures that should be possible to fabricate that are getting close to that. And we showed that there are other directional emission approaches that could be used for even further improvements in performance. So in short, we showed that although it's obviously very challenging to combine optics with other domains of physics, like the electronic properties of materials, and like thermal transport and mechanical properties like tension and resilience, mechanical spring performance, all those can be done. And when we start to combine things together, we enable all kinds of interesting new applications that we would not necessarily be able to appreciate just through a pure traditional photonics capability or framework. And so in short, the point is that learning about new physical problems and then combining those with nanophotonics is extraordinarily powerful approach and should serve you well in the coming decades if you get involved with this field. So want to thank all of you for sticking around to the end of the course, and I hope that you've enjoyed everything about the course. Please feel free to contact us through edX if you have any questions or comments after you're done. Thanks.